Good afternoon, everyone. Please could I ask you to keep your cameras turned off and your mics off as well, please. I'm Tony Oskilly. I'm a co-director of Durham Energy Institute and also the director of the UK National Clean Maritime Research Hub, which is coordinating the research activities across 21 UK universities to decarbonise the maritime sector. Shipping is essential to global trade, but it is quite difficult to decarbonise. And although there's significant work going on in terms of the scale up of alternative fuels, that will be critical to the long-term decarbonisation strategy. These are not available at the scale required, and also are more expensive. So energy efficiency offers a practical near-term pathway for the decarbonisation of the maritime sector. It can reduce fuel use, cut emissions, lower cost, and also prepare the sector for future low carbon fuels. So this talk this afternoon will outline the regulatory drivers, the key efficiency measures, the emissions reduction potential, and the incentives and barriers affecting the uptake. Dr. Richard Williams is a mechanical engineer and postdoctoral researcher in the Department of Engineering at Durham University. He's the MOL Research Fellow for the UK National Clean Maritime Research Hub and a Fellow of the Durham Energy Institute. He's going to give his presentation, and then we'll have the opportunity for Q&A at the end. So over to you, Rich.
Thanks, Tony. Hopefully you can see my slides now.
Yes.
Brilliant. So thanks for the introduction. So yeah, my title, or my presentation is entitled Short-Term Greenhouse Gas Emission Reduction in the Maritime Sector and the Role of Energy Efficiency Measures. So, as Tony just said, maritime transport carries most of the global trade, but remains difficult to decarbonise. Maritime transport is a significant source of global emissions, sort of 3% or so of global CO2 emissions, and currently is fueled by marine fuels, particularly heavy fuel oil and marine diesel. Those emissions include CO2, SOx, NOx, and particulate matter. So we're not just looking at CO2, but air quality as well. And reducing emissions in shipping is essential to meet international climate goals and limited environmental damage. So the International Maritime Organization aims for a 20% reduction by 2030 and net zero emissions by 2050 for the ship industry. So that's the goal being set by the overarching organization. So shipping is traditionally a conservative industry, generally due to long asset life cycles, high safety requirements, high capital costs, and operational risk associated with global trade and fragmented ownership structures. There are often split incentives, so owners pay for capital upgrades, but operators benefit from the fuel savings and efficiency gains from those upgrades, so neither gain their full benefit. Ships also operate over long distances and in global markets, which requires global fuel availability and reliable port infrastructure all around the world. So a whole system approach is required to net zero in shipping. So these may be vessel design and efficiency changes, so energy efficiency like we're going to talk about today, ship design, there are maybe technological solutions or efficiency solutions. Ports and vessels also need to decarbonise, and that needs infrastructure support, so shore power, clean fuel bunkering, efficient port operations, reducing the carbon footprint of assets, which may be electrification of those assets. So the supply chain also needs to be decarbonised, so sustainable logistics, taken into account supplier emissions, and that all requires lots of data and transparency amongst the different players in the market. For fuel transition, we need also an energy transmission, so transport transitions, so marine fuel scale up. We need new renewable electricity for e-fuel production, all at high safety standards, and ports to act as energy hubs in a new market. All of this will require policy, regulation, and finance. So strong regulation, green finance incentives, and support, and also global collaboration around the world. So the enablers of net zero really is innovation, both in the technical and solutions, data and digitalization, a workforce and skills piece to do as well, and infrastructure and committing to those assets for the future. So why efficiency first? So this is one pathway to decarbonisation of the maritime sector. So very much looking at efficiency first. So maximising efficiency and reducing energy demand today through operationals, technical, digital and electrification, and also putting in place that support structure and the market and regulatory structure for achieving net zero by 2050. So that's really what we're doing now in the next sort of 10 years. In midterm, so looking at 2030 to 2040, this is really where we're looking at fuel scale up, and fuels are biofuels, e-fuels, LNG, and electric e-LNG, green methanol, green ammonia, green hydrogen, and also carbon capture and storage. All of these will have a role to play, but need large infrastructure expansion, large bunkering availability, and also engine readiness for the vessels of the future. And in the 2040 to 2050 time frame, we're looking really at a full fleet transformation, bearing in mind that vessels have a 25 to 30-year lifespan, so the decisions we make now will affect what is still around in 2050. We're aiming for a full net zero ecosystem, which is mature, largely based on zero carbon fuels. So efficiency is first, as I just said, really for lower fuel consumption, which can help reduce operating costs. It means in the future we'll need less green fuel, which can be more expensive, and reducing that infrastructure need of producing those fuels. And it also has a quick impact now rather than in the sort of 2040s and 2050s. So there are quite a few incentives in the shipping industry. So there is a lot of regulatory and market pressure. So shipping industry faces pressure from the regulators, customers and investors to implement sustainable practices. There's some typical regulations here. So IMO I've already mentioned, but also EU has quite a few measures in place, and the UK as well. And it's just worth saying that these requirements will tighten over time. So they're starting off quite soft, but they will ramp up quite quickly. So by 2030, 2040, the shipping industry really needs to catch up. Just have a bit of a closer look at some of those regulations. So the International Maritime Organization sets the global regulatory framework for reducing greenhouse gas emissions from international shipping. So these are large-scale vessels, gross tonnage of 400 tons and above, which would typically be like bulk carriers, tankers, container ships, gas carriers, those sorts of vessels. Smaller inland vessels or coastal vessels tend to be handled by the country themselves. If you look at new ships, so there's a thing called the Energy Efficiency Design Index. So this is the minimum requirement for new vessels. This is really encouraging new propulsion and new designs to be implemented in new vessels. There's for existing ships, there's a thing called the Energy Efficiency Existing Ships Index. So this requires technical upgrades or engine power limitations. So it's bringing older vessels into compliance. So if they don't meet a certain standard, then they have to submit what's called a ship energy efficiency management plan and basically show how they're going to improve their energy efficiency to be allowed to continue sailing. There's the carbon intensity indicator, CII, which is really about operational measures. So every year the ships have to say what their CII rating was, and poor performers must improve operational efficiency or face penalties and restrictions in the future. And these tend to be done on a fleet basis rather than a individual ship basis. And then the final one on here was the IMO Net Zero Framework. It's not yet ratified, but it's a global fuel standard and a GHG emission pricing mechanism that the IMO would like to roll out around the world for improving the uptake of new fuels. It's important to say that that's on a sort of a well to wake type basis, so it's a full life cycle assessment of the emission of those fuels, not just the tank to the wake. In the EU, there's a thing called the Fit for 55 UK climate package, which is targeting 55% emission reduction by 2030. And within that is the EU ETS, which came into effect in 2024, and it puts carbon pricing on ship emissions and creates a direct financial incentive to reduce fuel usage and switch to low emission options. It's Fuel EU Maritime, which is promoting cleaner fuel, and that's from January 2025. And that requires progressive reductions in fuel intensity. So again, that's on a well-to-wake basic, and it's also requiring shore power. So while vessels are in port, in the EU, they'll need to be able to plug in the future. In the UK, we have the domestic maritime emissions will be included in the UK emissions trading scheme as of July this year. And the UK and EU are working towards linking their emission trading schemes together. So that will be in the future. So as I've already said, our decarbonisation options really in the long term are alternative fuels. So these are things like hydrogen, ammonia, methanol and biofuels, but they require significant scale up. Some of the other challenges include the lower volumetric density of the fuels, so larger space requirements on board vessels. They tend to have lower technology readiness levels at the moment, and they have unfamiliar sector safety implications. So the implications of putting things like methanol or hydrogen or whatever on board a vessel are not yet fully understood. There's also carbon capture, utilization and storage, so capturing the emissions of existing and new fuels, and it may be a pre or post combustion technology. Again, that they tend to be at lower TRL level, and there can be challenges around space and energy requirements on board vessels, including the storage of the CO2 once you've captured it. So that would allow the prolonged use of existing fuels. And then finally, our energy efficiency measures. So these should be adopted first, as they reduce fuel consumption and the operating cost. So really the background to my presentation today is that back in 2024, we were asked by DFT, the Department for Transport, to write a report assessing the evidence for energy efficiency measures in maritime. It ended up being a very long report of 95 pages where we gave an overview of the regulations, maritime decarbonisation and the relevant abatement measures of greenhouse gases. So as a systematic review of each energy efficiency measure in turn, where we gave an explanation of the measure, estimated the reduction potential and the technology readiness of those measures. So and what sort of vessel they would be applicable to. So whether they're applicable to a small vessel, a large vessel, etc. So that report is publicly available, and if you can't find it online, I'm sure we can help you find it if you're interested. So if we look at the sort of the options of energy efficiency that we can obtain, they change whether you're looking at an older ship or a new ship or an operational measure. So if we're looking at new ships, we may choose to alter the vessel propulsion and power, or add waste heat recovery, or look at the ship hull design. These are measures that are quite expensive to implement or retrofit onto existing ships. On an existing ship, we could look to replement something like a supplementary power source, like wind assistance. We may choose to alter our rudder or our propeller and flow conditioning devices. We may choose to alter the coating of our vessel for biofouling, for example, or we may choose to upgrade our energy management systems. There are also operational things we can do, either on the vessel or in the port. So the incentives, there are for implementing energy efficiency measures. They can be fuel cost savings, so reducing the fuel consumption and lowering our operating cost. There may be regulatory compliance, like I've just talked about. There may be port incentives, so there may be discounts for energy efficiency or low emissions vessels, such as reduced port fees. There may be market competitiveness, so charters may prefer ships with strong CII performance, which could improve your charter appeal of your vessel. There may be emissions trading benefits, so lower your penalty exposure for your reduced emissions and reduce your carbon costs. Or there might be corporate reputation, so demonstrate commitment to sustainability and enhance the public image of your company. There are quite a few barriers to implementing the energy efficiency, though. So as we've already said, vessels have long lifespans, so 25 to 30 years, which typically can delay your fleet transition. Some of these technologies are not very mature. There are many low carbon solutions, but you're not yet commercially scalable, which limits the large scale deployment. There may be operational safety concerns. New systems must meet strict safety and reliability standards for insurance purposes, which can increase the hesitation of ship owners when they're choosing their new vessels. There may be infrastructure gaps, so limited ports with shore power or alternative fuel supplies. Very few ports currently have things like hydrogen in place, which would restrict your implementation. There may be split incentives between the owner and the operator. These efficiency measures can have very high capital costs, which can basically not have a business case. And there can be regulatory uncertainty as well, so inconsistent global regulations and evolving IMO changes. So that can reduce your investor confidence for releasing cash for implementation. When we did our survey and we looked for evidence of the emission reduction potential of these technologies, we looked at lots of different literature sources. So these are brochures, academic papers, online resources, classification societies. Quite often grey literature, as there's not a huge amount of peer-reviewed papers of these measures actually on board vessels. The data is often commercially sensitive, especially when a service or technology is being sold by a company, and it requires deep understanding of the application and the particular ship. There may be no mechanism to share any data in a meaningful way of each of those technologies. So we really had to rely on several sources and assess the quality of the data of each of those sources. It's worth saying there are numerous energy efficiency potential reviews around. They generally have broad agreement that the estimates have a wide range, and often rely on statistical methods to sort of assess the quality, really aiming for a medium rather than a minimum or maximum energy efficiency saving. couple of sources here. So on the left-hand side is an image from the World Bank report. This is a recent report, I think it was last year, where they looked at each of the sort of energy efficiency saving technologies and tried to estimate their emissions abatement. So if you look at the plot, this is an emissions abatement curve. So the things in green are generally quite costly to implement, that they don't cost very much, but you can have a significant CO2 saving from implementing those. So they're the ones that you should probably always do. And on the right hand side, they can save you a large amount of CO2, but they maybe cost too much to implement. And in there, things like waste heat recovery, there may not be a business case for retrofitting that, say, onto an existing vessel. So that's one way of looking at it. That was a very detailed report by the World Bank. There are also some technology trackers. So on the right-hand side is the DND Energy report. So every year they update this report, looking at each of the technologies and sort of how, the maturity of those technologies. In academic papers, there's two examples here. So on the left from 2017, they use a box and whisker type plot to look at all of the available literature sources at the time, and listed all of the different measures. So I mean, we can look down here. So speed optimization can go anywhere from close to 0% saving all the way up to, say, an 80% saving. So there's a large spread of data. The one on the right-hand side is a very recent report. This was actually a report done by the Hub, and in here they included fuels as well. So there's a lot more data than back in 2017, and it's a much more detailed sort of report. What you can see from here is that the fuels, they included fuels rather than just energy efficiency. They have the really high CO2 emission reduction potential. But again, there's a really large spread, so anything from very small reduction potential up to almost 100% reduction potential by, say, implementing methanol. So they really rely on, applying statistical methods, and in this case, it's box and whisker plot to really show what could be achieved by implementing each method. From my report, I did a very similar, but I didn't do the statistics, and really there's a very plot in the middle is my version of those, and they're quite similar really in what can be implemented, the highest efficiency saving technologies and the lowest. It's worth just dwelling a little bit on how we would estimate efficiency improvement potential, which can maybe explain quite a lot of the spread in that data. So, if we want to estimate the efficiency, we could look at, say, modeling. We could use some simulation-based prediction of energy savings, but this can really rely on a lot of not guesswork, but the error can be quite high in your modeling. We could do some laboratory testing, say like tow tank testing or things like that. Tend to be very controlled testing environments of individual technologies in isolation, or we could do the higher cost field trials, so implementing these on real vessels and trying to estimate the efficiency improvement on a real vessel. It's worth saying that external factors change. No two voyages are the same. Wind conditions change, so it makes it quite hard to really estimate what the efficiency improvement was. You really need to have it on board for a significant period of time to estimate that improvement. It's also worth looking at how to choose a baseline for the improvement potential. So if you choose a poor baseline with a really low efficiency of your vessel, you implement your device onto it, you can over predict the efficiency gain across a fleet. Whereas if you choose a state-of-the-art vessel as your base case, then you could under predict the potential improvements at a fleet level. So again, you really need to understand the sort of the details when looking at the sources. Energy efficiency measures combined are also compounded and not additive. So if you put all of the energy efficiency measures that you have onto one vessel, it won't add up to your 10% plus 10% plus 10%. It will be somewhere you get diminishing returns from implementing those new technologies. So there's quite a fine balance, and it really requires in-depth engineering knowledge and design to sort of predict your overall energy efficiency, or what you will end up with on your vessel. So this slide shows all of the measures that we included in the report. There are sub-measures under each of these. I'll not go through them in detail, but generally you group them in vessel propulsion and power measures, waste heat recovery measures, ship hull reduction measures, propeller and flow conditioning devices, lots on operational measures, and then measures while in port. So they were the overall groupings. I'll now go through some of those in a little bit more detail. So if we look at our propulsion systems, what we could do is turbo compounding systems, so applying energy recovery in the exhaust. So you're converting that waste heat, similar to a turbocharger in a car, to boost your fuel efficiency. They weren't standard sort of 20, 30 years ago, but they probably are more standard now on modern vessels. Hybrid propulsion systems, again similar to a car, so you may choose to run your vessel in electric mode or a engine mode or a hybrid mode in between the two, depending on the voyage that you're taking part in. The order books, not all new vessels are hybrid propulsion systems, but they are becoming much more common. And then finally there, you may choose to have a fully battery electric propulsion system on board, but again, that's really for short duration shipping, not long duration sea shipping. So the sort of ferries and those sorts of things may be able to switch to fully electric propulsion. There can be further advanced energy systems, such as using fuel cells, so hydrogen or methanol-based fuel cells for power system, for powering your auxiliary systems, for example, or propulsion in some cases. They can provide zero-emission energy solutions on board your vessel. You may be able to implement solar energy on your ship. So if you have large deck space that isn't being used for something else, you could put solar cells on there and power your auxiliary loads from those cells rather than from your main engine. Smart energy management, you can upgrade your smart systems to optimize those systems, similar to a building, say. And you may choose to implement low energy devices. So things like LED lighting, again, 20 years ago, that wasn't normal on a vessel. Today it is, but you could choose to retrofit those older vessels with LED lighting, and you could significantly lower your energy usage. Similarly, with variable frequency drives for motor controllers or air conditioning, heating, you may choose to install heat pumps, for example. Wind-assisted propulsion is one of the big ones, can have significant savings in industry. I've seen up to sort of 20% efficiency savings from this alone. The wind-powered devices reduce the fuel use by supplementing the engine power, so you can run your engine at a lower power if you deploy these devices. The fuel saving is very dependent on the voyage profile itself, where you're sailing in the world, what the weather conditions are like, what the sea state is like, the wind speed, and obviously the direction you're sailing in. So the challenges are wind variability and weather routing, so really predicting what the weather is going to do, so you make sure that you sail a voyage that can maximize the use of those devices. It needs integrating with the ship design, so for a new ship that's a bit easier, but retrofitting it onto an existing ship will likely need a lot of steel to do so, a lot of shoring up of that vessel. which requires large upfront installation costs, and maybe there's not really at the moment the incentives in the marketplace to do so. The vessels with it at the moment tend to be sort of I think first movers, I suppose. Technologies, there are a number of these, things like Flettner rotors, which are spinning cylinders, meaning the wind direction doesn't matter so much. Rigid sails, wing sails, suction sails, which are like aeroplane-like vertical sails, a bit like sailing vessels. A lot of these require additional power supplies, which can be quite significant, especially with the Flettner rotors. And then the final one there is kites. So kites that can sail above the front of the vessel and drag your vessel along with a tailwind. Moving on to waste heat recovery. So energy is usually wasted through heat. This is really looking at the engine, the main engine. If we recover that normally wasted heat to generally useful power, it increases the overall efficiency of the vessel. So we may look at the engine exhaust or the engine cooling water, the two of the big sources of heat. Some of that heat is at low temperature and some of that heat is at high temperature. So at a higher temperature, you would probably use a steam-based recovery system. And at a lower temperature, you may choose to use an organic Rankine cycle system. But in both of those systems, you would convert that power into electricity, and you could use that electricity for hotel loads or propulsive power. Moving on to the hull design, so we have optimizing the shape of the hull, which has a direct impact on the resistance or the drag of the ship moving through the water. If we reduce the block coefficient, it lowers the water resistance and improves your propulsive power. So the block coefficient is a way that people look at the shape of the ship. So on the top left is the equation for that. Basically, the more streamlined your vessel is, the lower the drag. It's worth noting that when you look at hull designs as well, really, now that we have modern processing tools, we can do multi-objective, take into account lots of different things to really optimize that design for higher efficiency and lower fuel usage. Moving on to air lubrication systems. So this is where bubbles are injected beneath the hull to reduce the skin friction between the hull and the water. Again, it needs power to power the compressors, and there are installation and maintenance costs. These can be implemented on existing vessels or new vessels, and they tend to be vessels that move relatively fast, like cruise liners that are implementing them. So these air lubrication is implemented on quite a few vessels today. Moving on to hull coatings and anti-fouling. So biofouling below the waterline increases hydrodynamic resistance, driving up fuel consumption and emissions. So you basically, barnacles or things stick to the hull, which it increases the amount of fuel used when passing through the water. It really depends on the sort of the operational profile of the vessel. If you spend a lot of time in port, then you will have higher fouling than if you spend lots of time at open water. The effective coatings maintain the hull efficiency, reducing operating costs and the environmental impact. So there are a number of different coatings that are in use today. So biocidal coatings, these leach a biocidal agent into the water, killing and fouling the organisms as they attach to the vessel. There are issues with their effect on the wider maritime environment, and so there are regulations around the use of these. There may be fouling release coatings, which have a low friction, making it really difficult for marine organisms to be attached to the surfaces. And then finally, there may be hard coatings. So these don't really inhibit marine growth, but instead allow for regular cleaning of the vessel. So your choice of those sort of coatings will very much depend on the type of vessel and where you're operating in the world. There are already also quite a few emerging innovations in coating technology, so conductive coatings, slippery liquid infused surface coatings, photocatalytic, physical biometric and chemical secretion coatings are all very much a lab or early pilot scale type coatings. There's lots of work traditionally around the propeller and the rudder, things like pre-swirl ducts, contra-rotating propellers, vane wheels, and boss cap fins, and optimized rudder designs. None of these are particularly new ideas, but they just haven't really found widespread use in the industry. But they are certainly commercially available and readily available. Moving on to operational measures. So you have things like ballast, draft and trim optimization. So this is how the vessel sits in the water, can have a significant impact on the drag of your vessel and the efficiency of your vessel. You may choose to undertake some speed optimization, so efficient speed profiles, reduce fuel by matching vessel speed to the engine load, so operating your engine at a much higher efficiency point, depending on the environmental conditions. I mean, overall, if you reduce the speed of the vessel, you reduce the power required to push it through the water. Weather outings, so using real-time weather data, vessels can avoid adverse conditions. Maybe you can sail downwind or things like that. So lowering your propulsion demands and increasing your efficiency. And then finally on here, just in time arrivals, so minimizing wait times at anchor outside the port by sailing at a slower speed. The issue here is that the ship and the port need to be in communication to know exactly when the berth is going to be available for the incoming vessel. And obviously the ship doesn't want to miss that berthing time either. So there's quite large complexities about just-in-time arrival, including the contractual agreements and planning and data sharing across the industry, really. And finally, voyage and engine optimization. So this is really applying all of the above using advanced algorithms and planning efficient routes, while engine derating and ballast adjustments improve the efficiency. So doing all of the above in taking smart decisions. Hull maintenance and shore power, so hull cleaning and polishing. So yeah, so these are the options of vessels while they're in port. So regularly cleaning that vessel. Not all ports can clean vessels because of what's it called? So bringing new organisms into new coastal regions. But where you can, then they should be able to clean, and they can. Shore to ship power, so plugging in the vessel during port stays, so provide the ship with electricity, and this allows the engine to be turned off, eliminating emissions from onboard generators, helps vessels comply with port emission regulations. The power consumption of a vessel in port can be quite large, so in the order of 10 megawatts per vessel is common, which could power between 3,000 to 7,000 homes. So the reason in the UK certainly why lots of vessels aren't plugging in at the moment is the power requirements and the upgrades required to power those vessels, and the infrastructure costs of putting in those cables as well. And then the electrification of equipment in port, so all the cranes and the vehicles, etc., need to be electrified. The challenges again here are due to the infrastructure availability of the electricity connection, and the potential for, just to note that there's a potential here for clean power generation within the port as well. So where a port can't upgrade their electricity supply, they can look to generate clean power within the port. That could be from a generator, or it could be from, say, a small nuclear reactor or sort of something like that, or renewable energy, wind, solar, etc. So really, as I said before, there are incentives to implement these energy efficiency in shipping. So the fuel and cost savings of each of those measures, regulatory compliance, port incentives, market competitiveness, There may be emissions trading, government support, or corporate reputation. So key takeaways from what I've said so far. So energy efficiency can significantly reduce fuel consumption with immediate impact, and it cuts fuel use and emissions, reducing operating costs and supporting climate goals. There are a wide range of solutions, from operational to hardware. Choices depend on the specific vessels and its operational profile. And these measures are compounded and not aggregated, so it requires a complex understanding of the interactions. Efficiency measures are a foundation for innovation, as it improves readiness for alternative fuels and advanced maritime technologies, and it can offset the increased cost or space requirements of alternative fuels. Operational measures have significant potential and are likely to be adopted first, so immediate impact. They can be cost effective, they can be scalable, but they do require incentives to implement. If you look at hardware solutions, they can have immediate impact as well. So some retrofits, for example, hull coatings, propeller upgrades are quick wins, but others require major overhauls or new buildings. Strong incentives are needed now, so long vessel lifespans mean decisions today affect 20 to 50 targets, but there may not be a business case or access to cash to upgrade older vessels towards the end of their lifespan. Energy efficiency for regulatory compliance. So implementing energy efficiency helps meet regulatory compliance, such as those of the IMO and other agents, ensuring compliance to avoid penalties, which is tightening over time. And a lot of these efficiency measures can be included in the energy efficiency management plan. It's worth saying as well that the UK government is investing significantly in this area, so there are 2 calls open at the moment. There's the Clean Maritime Demonstration Competition Round 7, which is 121 million deployment trials, pre-deployment trials or feasibility studies. And there's ZEBI2 as well, so zero emission vehicles and infrastructure, which is £150 million plus as well. So they're the 2 calls, and the 2 open at the moment. When I gave this presentation originally to DFT, I was asked to provide some policy suggestions, and I decided I would keep them in here as well, just they might be interested with this audience. So a way we could improve the uptake of efficiency measures could be to provide installation incentives beyond fuel savings, so ensuring technologies are clearly credited in carbon reporting and crediting linked to verified savings. We could incentivize hardware retrofits, especially first movers, so promote energy efficiency technologies through grants or tax relief for retrofitting existing vessels. We could incentivize green freight contracts with cargo owners, so support contracts that share fuel-saving benefits between owners and charterers, because split incentives are a major barrier to efficient investment. We could incentivize operational measures, so encouraging speed optimization, weather routing, and just-in-time arrival through regulatory frameworks, financial incentives, or green corridors. These require minimal capital investment and can deliver quick emissions reductions. Requires tackling contractual norms such as due dispatch, which is what makes it quite challenging. We could promote the installation and the energy requirements of shore power, so expand port infrastructure for shore to ship power to reduce emissions during berthing, and this requires significant investment in grid connection upgrades or local port power generation. We can provide data transparency and market pull, so require ships to publicly report fuels and efficiency data when calling at UK ports. Cargo owners could then prefer efficient ships and pay green freight premiums. And then finally, green ports, so encouraging UK ports to offer discounted port fees for efficient ships with energy efficiency technologies such as wind-assisted propulsion. So that was my final slide. Thank you.
Thanks very much, Richard, for a very interesting presentation. We've got time for some questions. I seem to be visual being on the screen here.
Oh, sorry, Tony.
Yeah. So, does anybody want to ask any questions at all? Maybe I'll kick off, Richard. Thinking about obviously this was a piece of work that we kicked off initially at from a hub perspective. What do you think needs to be done now? What additional work needs to be done to kind of identify the best low-hanging fruit that the maritime sector could adopt?
I think really, yeah, looking at the uptake of these efficiency measures from a sort of a order books point of view, where the UK is strong, looking at what companies there are in the UK, what gaps there are in the UK, would be a good place to start.
I don't know whether you've got the chat open, but Alessandro has asked a question in relation to the ORC and ranking cycles not that cost effective, I guess. Has using waste heat directly for cooling or cooling and dehumidification being considered instead? And do you have a sense of how that might compare given the cooling demands of vessels?
So, well, using waste heat directly for, say, cabin heating, I'm sure is used already on vessels. For cooling, I don't think anyone's doing that. So most sort of reefers now, the individual containers have are sort of plugged into electrical systems, so they have their own cooling systems on each of the electrical cooling systems on each of the containers. So certainly something that would be interesting is how you could directly use the cooling for those systems. Cooling for hotel loads, yes, definitely we could look at that.
Yeah, I guess Alessandro was kind of alluding to air conditioning, I guess, that side of things, and of engine rooms and accommodation blocks, etc.
Yeah.
Collins asked, has the UK any electric powered coastal ferries? Isle of Wight, for example. I know that Norway has.
I'm not aware of any in the UK at the moment. Maybe there are some fully electric workboats, but not coastal ferries, I don't think.
Yes, so actually the ferries to operate between Dover and Calais, that they're shifting towards electric battery vessels at the moment.
Yeah, I think they've ordered them. Is that right, Tony?
Yeah, that's how I understand it, and I guess the big problem is that it's the charging infrastructure that is the issue, and yeah, I think Claire's put in the chat about the investment that's gone in from DFDS in particular.
Yeah,
so it is something that's happening, but I guess the thing that's restricting that shift is grid power, and that's the similar thing that's hindering the take up of cold ironing shoreside power for vessels in ports.
yeah.
Any other questions? Here we go. Do you have any observations on the organizational incentives, business cases shaping technology adoptions?
Do you have any observations on the organisation? I'm not too sure what the question is. I mean, I guess, yeah. So there are incentives from financiers to adopt greener technologies. There are green finance available. It really is being driven very much by the regulatory framework at the moment. So the IMO and the EU and the UK to some extent. Anything to add there, Tony?
Yeah, so I think a lot of actually pull is by for shipping companies is by their customers, and not that are kind of putting in place kind of demands to shift towards greener operations. Again, there's pressure from that side. It's not massive in the sense, because at the end of the day, like freight rates are very low, and measures almost invariably add cost, and that's capital costs, and the kind of, I guess, the payback period associated with that is a big influence on the decision making. But there are lots of examples of there was colleagues at Newcastle University's new propeller design being adopted and demonstrating. I think actually what will drive this mostly is by demonstration of technologies, and that's why DFT's UK Shores program in terms of CMDC and ZEFI and that are very important, because they're actually demonstrating the efficacy of adopting new methods, new technologies.